Well, good evening. I'm Charles Schultz, and this is the Randomizer. And tonight's term is going to be magneton. Now, that is a unit, just like a yard or a pound or a Tesla. It is a specific measurable amount of something, in this case, the amount of a magnetic field, but in specific applications. Um, we're going to talk about the magneton, what it means, and well, just what it takes to define one. So, first of all, I'm going to talk to you about our website, the Universe Science Center, and SchultzLaboratories.com. We have numerous exhibits, galleries, and rooms with interactive content that allow you to study such subjects as spaceflight or genetics or robotics, logic gates. What we're trying to do is expand the number of galleries we have and the interactive content we have. And by joining and becoming a supporting member of Schultz Laboratories, a student membership would take us a long way if we get a number of people to do that. And what that does for us is adds more content, more galleries, and more interactive displays. And if you wish to teach using our virtual world system, you can get your own gallery to display your work and a classroom where you can share your expertise with people all around the world. So this is a win all the way around. It's an interesting three-dimensional virtual world that you can walk around in and enjoy the exhibits and learn from. So even if the schools are closed, you can come right into our virtual world and learn all sorts of subjects. And if you're homeschooling, get with us and we put galleries in with specific content tailored to your needs. And if you want to run a company and you need training for your individuals, we can see about that as well. Join us for the Randomizer every 6 p.m. Eastern Standard Time on weekdays, where we pick a random technical subject and cover it briefly and in enough detail to give you an understanding of some of the concepts of physics and science. And 9 p.m. Monday on Eastern Standard Time, we're doing our robotics classes. We're up to class 4 coming up this following Monday. And we're covering such subjects as senses and movement, models for robotics, and all sorts of things, soldering methods. I think you'll have a lot of fun with it. You should join us. Click through the Schultz Laboratories classes, sign up, and learn something fascinating. So let's talk about magneton units. A lot of people aren't aware of the connection between electrical current and magnetic fields, and it's actually a very simple and direct one. If you were to take a battery and a loop of wire and run a current through that loop of wire, you would create a magnetic field all around that conductor, that loop. And if you make many loops of wires wound together in what's known as a solenoid, then each loop adds to the strength of that magnetic field. And 1,000 loops can easily pick up nails, pieces of metal, or whatever. When you see these huge machines with the magnets dragging the metal and dropping it in the furnace to melt it down, you can be absolutely assured that the thing that's doing that picking up is a huge magnetic coil, a solenoid, with an iron core. So the movement of current creates a magnetic field. Likewise, a changing magnetic field by a conductor induces a current in it. So what are the smallest possible charges that you can move around to create a magnetic field? Well, think about it. Any electric current is simply the movement of charges, charged particles, typically electrons, but protons can do it also, although not quite as effectively. Electrons are tiny negatively charged particles, and they carry what's known as the unit of electric charge. You're not going to find a fraction of a charge on anything smaller than the 1 unit of charge. The only exception is within some of the particles themselves, such as protons and neutrons. They're made of smaller particles called quarks. They have fractional charges, but that's a different story. You'll never see a free fractional charge in nature. So the unit has 1 unit of charge, the electron has 1 unit of negative charge, the proton has 1 unit of positive charge. These are basically the smallest charged particles you can move around under control and do something with. So, what is the smallest unit of movement that an electron can have, for example? Basically, it's going to be one of two things. We can see the spin of the electron itself, its spin moment as it's called, or we can see the movement of the electron in an orbit around an atom. And it isn't like a planet going around quite. It's more like a movement of a cloud. It's sort of counterintuitive. But here you have a tiny particle with a charge moving in some measurable, predictable manner. So the magneton for the electron, also known as the Bohr magneton, after Niels Bohr, the physicist, the Bohr magneton is a unit of charge based on the mass of the electron, the unit of charge, the spin that it has, or the path that it's following, and a couple of other small physical constants, such as the reduced Planck's constant, which is based on the smallest unit of energy or space-time, depending on implementation. So this tiny unit of charge and movement creates a measurable, solid, quantifiable magneton, a unit of measure. So just like you'd say you have a cup of sugar or a quart of milk or a pound of sand, you can say you have one magneton of charge. So how much is it? Basically, it's about 9.27 times 10 to the minus 24th. That's a trillionth of a trillionth amps per square meter. And a meter is a little bit larger than a yard. So that's an incredibly tiny amount of charge. And yet, when you think about it, there are trillions upon trillions upon trillions of electrons in a very small amount of matter. So this can add up sizably and give effects such as a magnetic field in a bar of metal or an actual magnet itself, which is made by aligning all the Bohr magnetons, all these paired electrons, so that their fields add up uniformly, just like the loops of wire in a solenoid. So these fields can contribute to each other and build up sizably. Now, the proton, being a charged particle, also has a magneton, a tiny unit of magnetic field strength, but counterintuitively, even though the proton is a much more massive unit, its field is almost 2,000 times smaller. Its magneton is almost 2,000 times smaller because it's divided by the mass of the particle. A proton outweighs an electron by about 1,836 times. So the particles that make up a proton with one unit of positive charge are 1,836 times plus more massive than an electron. So when it comes right down to it, for density of charge versus mass, the electron is the king. So being the lightest particle, yet having the same amount of charge as something as large as a proton, it wins hands down in sheer magnetic field versus mass. So now, what's interesting is we always use electrons as the units of carrying our electrical power or current. Why is that? It's actually because protons are usually not free to migrate. They're tied into the nuclei of the atoms, and the atoms are locked together in a solid or in a liquid and don't generally get around a whole lot. So the electrons, being on the outer shells of the atoms, can migrate around fairly freely. If they couldn't, we couldn't have chemical bonding and we wouldn't exist. So, interesting thought. The more massive particles, the protons, can carry a current, but it takes 1,800 plus times more power to move the current in the form of protons than it does in electrons. So again, electrons, by being lightweights, are the king. They're easiest to move. But here's something to think about. Some materials can actually conduct protons, and ice, water ice, can do this. So it's possible to make a conductor out of water ice that literally conducts protons along to carry a current. It's an unusual system, but it can be done. Is there another way to conduct a positive electrical current and it will have the opposite magneton of an electron? Absolutely. Positrons, the antimatter equivalent of an electron. You really could use positrons as electrical current carriers, but there's not much matter you could put in them without them exploding into gamma radiation, because positrons and electrons tend to spiral towards each other, forming a type of matter called positronium, which only exists for a few microseconds at best, and then flashes into a burst of gamma radiation. 2 or 3 gamma rays, in fact. And the total energy of those gamma rays will be 1.02 million electron volts, because that's how much energy it takes to make a proton and an an electron and a positron. So now, the magneton is the unit, the tiny piece of magnetic field strength defined by the particle. Now, there's also a nuclear magneton. It's often referred to has either the proton's magneton, the one I mentioned earlier, or if you take the neutrons and protons in a whole nucleus as a composite entity, you can also calculate a magneton for a nucleus. So each element and each isotope has a different value of magneton, which is again the amount of magnetic field that you'd expect it to have, based on its charge, its movement, and its mass. One other thing stands clear. You would think that only an electron or a proton, this sort of charged particle, would have a magnetic moment. This isn't true. Neutrons, which are slightly more massive than protons, 1,838 instead of 1,836 times the mass of an electron, neutrons are neutral and do not have an overall electrical charge, but they actually do have a magnetic moment. Why would that be? How can something that's neutral and has no electric charge generate a magnetic field? The answer is interesting. Neutrons and protons are not singular components. They are not fundamental. They actually are composite particles made of smaller parts called quark particles. Every proton is made of 2 up quarks and 1 down quark. This is where we get to the fractional charges. The up quarks have a plus 2/3 charge, and the down quark has a minus 1/3. 4/3 for the 2 ups, minus 1/3 equals 3/3 plus 1. A proton that these 3 quarks make up has a plus 1 charge, but a neutron is made of 2 down quarks, which have minus 1/3, minus 1/3, and 1 up quark with a plus 2/3, and it exactly cancels to 0. So the net charge on the neutron is 0, but the components inside the neutron, the quarks themselves, have charges, and they have magnetons. So there is a net magnetic field that remains when you add up these internal moving charges from the 2 down quarks and the up quark in a neutron. This is one of those interesting things you find in nuclear physics or particle physics, that a counterintuitive result occurs. The total charges are 0, but there is a net magnetic moment. Well, how can that be? It's because the particles don't exactly overlap each other as they're moving around inside, and that's kind of a fiction too. It's a quantum mechanical soup. But they never completely overlap and therefore never completely erase the charge. So although it adds up to 0, they're kind of bumps and lumps of plus and minus moving around a neutron. And that is where its net magnetic moment comes from. So there is a magneton for the neutron. So that's an odd state of affairs when you think about it. Now, how could you apply it to anything in the real world? Well, you can, as a matter of fact, create a solenoid out of copper and have an iron core in it to strengthen the magnetic field. And you can hook a battery to it that has a known mass. And you can get the mass for the copper coil and the mass for the iron core in the middle of the magnet and the mass of the battery and add it all up. And then you can create the magnetic field in the solenoid by hooking the battery up to it. And you will end up with a device that has a net magnetic moment. Now, it's not the same because this device doesn't get it as a result of its intrinsic charge. The intrinsic charge of the device is 0. So calculating the magneton for a solenoid is quite different from what it would be for calculating it for an electron or a proton or even a neutron. But there is the capacity to do that. If you actually played games and charged the whole system with a static electric charge, then yeah, you could calculate a fake magneton for it. So here's a device, some wire, some iron, and a battery, and a static charge, where you can actually make a nuclear concept called a magneton, a net magnetic field, out of a simple device you can hold in the palm of your hand. Of course, it's not really significant, but it's just an interesting, stupid trick. So if anybody has any questions about magneton and the concept and how it works, please feel free to ask them. The floor is open. Meanwhile, I'm going to encourage you to go to schultzlaboratories.com, universesciencecenter.com, sign up and become a member. Get yourself an educator's class and gallery, display your works, share what you know of the world, or just march around and interact with things, go out on the planets, um, play with some genetics, play with some logic gates. Put your Oculus on, go in and wander around in an amazing virtual 3D environment. And pretty soon we're going to be adding some more to our space exhibits. More about that later. Ah, from Jim Diaz, does a large quantity of moving water have a field? Ah, that would depend. Moving water, if it is a conductor, moving through the Earth's magnetic field actually creates a current. It doesn't have an intrinsic field unless the current is flowing through it from an exterior source. But moving through the Earth's field, it creates what's known as an inverse sort of field, an eddy current field. So if the water is conductive and it's moving through a magnetic field, then it creates a net current of its own, which creates a magnetic field. In fact, this is something called the MHD effect, magnetohydrodynamic effect. Many years ago, somebody was experimenting on the River Thames and dropped a couple of electrodes in the water and measured a current going through the water as it flowed through the Earth's magnetic field. Later, this exotic effect was converted into a propulsion system for nuclear submarines to move quietly through the water. A charged field, some magnets moving in step magnetic fields would cause peristaltic motion. The water would flow through like a jet tube without any propellers or moving parts. Sometimes they will use a seeded, with potassium ions for instance, flame or explosion moving through some coils to generate MHD pulses of current. Now this is usually used for seismic work. Sometimes when you're studying the ground and the materials and veins and layers underneath, you'll set off something like an explosion of dynamite with acoustic sensors all over the ground, and then you'll measure the properties of the earth inside. Using magnetohydrodynamics, you can actually use this effect with something similar to a shotgun shell going through a solenoid, a big coil, and when it's detonated, it creates a burst of current which can be used to set off a number of sensors or effects in one shot. It was also used in some exotic testing weapons many years ago. So water can have a field, but generally if it's ionized or conducting and moving through a magnetic field. I hope that answered that question. I know I went far afield, but it was an interesting subject. Any other questions before we wrap it up? Okay, very good. Thank you, Jim, for the question. All right, well, I'm going to read my quote for the day at this point, if there are no objections. It is, "Trust in the Lord with all your heart, and lean not on your own understanding. In all your ways acknowledge him, and he shall direct your paths." And that's Proverbs 3, 5, and 6. Well, I know I sometimes seem to get my best inspirations when I stop pursuing a problem for some reason. Anyway, it's been an interesting discussion about magneton, and we'll have a new and different technical term tomorrow for the randomizer, and I hope that you'll join us live. I really enjoy having the interaction, and I think this is going to be a wonderful week, and I hope that everybody enjoys it as much as I have so far. So this is the end of the show. I'm going to wrap it up at this point. I'm Charles Schultz with the Randomizer, and as usual, make the world a better place. Thank you.